Hello, my name is Mitali Ramle and I'm a PhD student at the University of Potsdam, Germany. Today I will be discussing about our work in the recently published paper on the CGM and local group simulations. CGM of a galaxy encompasses all the typically low-density gas lying between the superdense interstellar medium and the superdiffuse intergalactic medium. This diffuse gas is extremely diverse in the temperature density phase space and hence quite complex in nature. The local group consists of a Milky Way Andromeda pair, along with a host of surrounding satellites and their CGMs. Its proximity to our frame of reference is one of the primary reasons which makes local group more suited to CGM observation studies. But on the flip side, the local group CGM observations are also highly contaminated because of the impending presence of Milky Way and its CGM constantly intervening between us and the quasar sightlines. This is exactly the juncture where specialized local group constraint simulations come to our rescue. They not only get the larger cosmological context correct, but also the local cosmography right. If we think a bit more carefully, we realize that the CGM observations have a substantial dependency on the local cosmography. In the study, we used three high-resolution realizations from the Hestia suite of constrained local group simulations. Our goal is to compute mock ion fractions and column densities for the local group CGM and see how they compare with existing observations. We first compute ion fractions for a set of 5 tracer ions using the cloudy ionization tool, and we input them into the HealPy package in order to create ion skymaps as shown here. These skymaps are generated from the point of view of an observer located at the local group center with the Milky Way M31 analogs on either side. We also generate radial ion column density profiles. As a next step, we pick up silicon 3 and O6 column densities from Fire 2 and Eagle simulations while we use Project Amiga survey results on the observational side for comparison. Beyond 1 virial radii, the simulated column densities are seen to drop much faster as compared to observations. We also include a comparison to two low-redshift observational datasets, Liang and Chen 2014 and Johnson 2015. One main reason to do this is to investigate if there indeed is any Milky Way contamination in the M31 observations. Our results are found to be in much better agreement with low-redshift galaxy data than with Project Amiga. Thus, there are some hints that Milky Way contamination may have contributed to some of the M31 column densities. To quantify this, we move on to explicitly model Milky Way contamination towards M31 sightlines in our simulations. We again generate sky maps, however, this time centered on the Milky Way rather than the local groups, so that's an observer's perspective, so to speak. We successively remove gas lying in layers from 10 to 150 kiloparsec from Milky Way center. Additionally, we also constrain the local group gas to be within 100 km per second of M31 systemic velocity. Now, in case of 1711 simulation, that's the middle panel, we see that a simple velocity cut effectively removes almost all intervening Milky Way contamination. This is irrespective of any additional radial cutoffs superposed on the existing velocity cut. We infer this from the clean overlap of all the different colored dashed lines. Nonetheless, column densities in 1711 are still very less as compared to observations, which means that our analog galaxies in 1711 are still underproducing silicon 3 and O6. The tail is quite different for our remaining two simulations. Here, the dashed colored lines do not overlap. That is, there is substantial Milky Way contamination at varying distances between Milky Way and Andromeda, which does not get eliminated despite the dual strategy of a radial plus velocity cutoff. Thus, from an observer's perspective, it is possible that some of the M31 sightlines are actually boosted due to Milky Way CGM gas clouds in the intervening space. That said, Milky Way contamination cannot be the only reason why simulations in general underproduce silicon 3 and O6 at large rate. There could be other reasons as well. Just to sum things up, the Hestia Andromeda analogs have cool and hot gas profiles similar to that from low redshift galaxy studies. However, they are at tension with the corresponding results from Project Amiga survey. If we include Milky Way gas, then in 2 out of 3 simulations, we are also able to reproduce increased column densities as seen in Project Amiga. Many thanks for your attention.